Me and all the other people you can see up there are planning to develop a tool for fair rankings in search, and we particularly are talking about web search here. And I'm going to give you a little bit of motivation why we're doing this, and then show you some recent work that we did about fairness in rankings. Then I'm going to explain a little bit how search engines work in general, and tell you then how are we going to work in this next year in the further research questions that we try to answer. Okay, so what we are concerned about is that if you have unfair rankings, you create like vicious feedback loops for the ones who are ranked. So imagine you have a headhunter who's searching for job candidates, and then you have a ranking algorithm that puts Mary at the bottom of the list. And then Mary is less visible for recruiters, and therefore she gets less job offers, which makes her getting less job experiences, and then she becomes less employable. And obviously then a ranking algorithm would put her further down on the list, right? All right, and we wanted to see if this actually happens in real life, and we tried to crawl LinkedIn data, and it didn't work at all. So we had to move to Xing, which is kind of the LinkedIn for German-speaking countries. And what you see here is a search result for various search queries, where the search queries are like on the top. So we queried for economist, market analyst, and copywriter. And you can see that the top 10 search results are slightly different from the top 40, and that they are very unbalanced in terms of gender. And what is particularly interesting is if you go to the lowest line, which shows you the data that is actually collected by the Statistisches Bundesamt, which is the Federal Office of Statistics in Germany. So this tells you that there is actually already a huge gap between the top 40 and the social real life in Germany. And then again, there is like a huge difference between the top 40 and the top 10. And it might be reasonable to demand that at least the top 40 and the top 10 should have similar proportions of gender. Okay, so what are we doing now? We want to incorporate fairness constraints into a widely used search API, which is Lucene and Elasticsearch. And why are we going for these ones in particular is because basically everyone is using it except for Google. So I just wanted to show like that basically everyone is using it. All right. So now I'm going to present you some of the work that we already did, and we are planning to incorporate like directly into Lucene and Elasticsearch or Solr. And that goes like that. So the first question we have to ask is, what is a fair ranking actually? And we define a fair ranking to be, given you have a ranking of length k, you have two groups of items so far. So one group is protected, the other one is somehow non-protected, and you have a minimum proportion of protected people you want to achieve, then a fair ranking is a ranking that in which the number of protected items does not fall far below this minimum proportion that you defined at any point in the ranking, right? So this is a little bit like abstract maybe. So given you have a P of 0.5, and you have red balls to be the protected group, then this is very clearly an unfair ranking because there is no red balls at all. And together with the fairness definition we gave, this would still be an unfair ranking because the red balls are all in the bottom. And a fair ranking would probably look somehow like that. And now, if we get a ranking, we want to be able to automatically tell if it's fair or not. And we developed what we call a ranked group fairness test for that, which takes the minimum proportion P as input. And then it compares the number of protected elements in every prefix of this ranking. And obviously the test fails if that number falls very far below the expectations. So now what you need is a comparison reference, right? And we take this, the expected number of protected elements to be created by a method that we call inherently fair, which was developed by these two guys in 2016. And what they actually do is they throw coins. So they use a Bernoulli process to create a ranking, and whatever ranking these guys create we call it to be fair. And we want our test to call all these rankings fair. Or what we say is like, because this telling every ranking what they create should be fair is very strict, so we say like, okay, we do allow a little bit of false positives, but it should not be more than this parameter that we call alpha. Okay, now the test is divided into two parts. The first one is called the fair representation condition. And what this does is very scary math, but the important part is the red part here. So what this tells you is, given you have a ranking of length k and p again, and you have tau p protected candidates in your ranking, then you take the cumulative distribution function of a Bernoulli distribution, which is the one that gives you the coin tossing example. And if this probability is greater than alpha, then we call this ranking that we just saw as fair. Okay, and the second part now comes, so you take this fair representation condition and you apply this to every prefix of the ranking. And the prefix is, you apply it to the first position, you apply the condition to the first two positions, to the first three positions, and so on, and you go through that until you have reached the entire ranking, and if the test never fails, then you say, okay, this ranking is fair. Now this becomes computationally very expensive, and you can also take the inverse and compute such a table that tells you, as an example, for p being 0.7, so I want to achieve 70% of protected people in my ranking. What this tells you here, this table, is that in the first position, I have to have at least 0 protected candidates such that my test doesn't fail. In the first 3 positions, I have to have at least 1 protected candidate such that the test doesn't fail, right? Okay. Okay, now I'm going to tell you a little bit how Lucene and search engines work in general, and then we will figure out where we can apply the method that I just described. So very, very superficially, Lucene works like that. You have some raw data, and then you have that you maybe crawl, or you have it from a database or whatever. Then you have Lucene that creates documents from it, where a document is not really like a file or something, but it's a Lucene document describes the data you have. So for example, in LinkedIn, a document would be a profile with all its information it has. So you would have like the name of the candidate, probably a picture, education, and so on. And from all these documents, Lucene builds a so-called inverted index, which is the mapping from words to pages. So it tells you, given I enter a search query, in which documents I can find these words that I just was searching for. And Solr and Elasticsearch are kind of like top-ons that are used in distributed systems. So if you have a very big platform, you obviously do not want to have only a single server, but you need to spread your index over a whole cluster so that you can serve many customers at the same time. And also, well, Lucene as well as Solr or Elasticsearch are using machine learning techniques, and so in all these parts you can try to infer fairness constraints there. Okay, so now what happens when a user issues a search query? So the search query is somehow parsed, and then it's passed to the index. The index retrieves some documents that it finds relevant, then it ranks the results according to some method, and then the result list is displayed back to the user. And this is where the method is currently sitting, that we already developed. And the first goal of the project would be to implement it in a way such that Lucene and Elasticsearch can work with it. Okay, so what are we doing? What are we planning to do in the next year is, so we have various points for fairness tuning. And just to showing you where in the picture that we just saw these are located is you can try to tune the document creation for fairness, which would be the red arrow right now. You can do it in index writing or query parsing. You can basically do it like everywhere. When you read the index, when you do the score calculation for the results, or even in the ordering of and the visualization. So, and then the project plan that we thought of so far is we have 2 main work packages, and the first one is to develop a plugin that implements the FAIR algorithm. So the first part is to study the feasibility of Solr and Elasticsearch so that we can choose for the better platform. And the first deliverable is the implementation as a re-ranking strategy. The second work package is to develop a plugin that is implementing a FAIR learning to rank algorithm. So that would rather be in the score calculation part. Then you would have as a first deliverable the algorithm itself. So we still haven't developed it yet. We are about to do that. And yeah, then we would have to implement it into Solr or into Elasticsearch, depending on the platform you choose. And that's it. Thank you. Questions? Do we have time for questions?
Do we have questions from the audience? Yeah, we could take one.
I'm Julia Stojanovic. I'm actually a person that you cited. And
nice to meet you.
We're both girls. We're not guys. So it's my student, Kay, and I. So this is very cute work. I wonder what it would take to extend this to more than binary protected group membership. So say that you have race or ethnicity.
Yeah, exactly. So well, we are currently working on that. I have a student who is writing a master's thesis about it. And yeah, we are planning to introduce that into the framework as well as soon as it's done. But we are about to having the, how you call it, like the proofs you need, and all the theoretical work is currently in progress. Does that answer the question? Or?
Not really, but I'm glad you're working on it.
Okay, I have another quick one.
Okay.
I think part of the discussions during the selection around your proposal, there were many people that felt that it's great to have a particular fairness metric being implemented in a real system. Can you hear me? Yeah, more or less. But many people felt that it would be great if you could somehow introduce into the system the computation of the fairness performance according to different fairness criteria. I mean, you're going to implement the one that is yours, but it would be, I think, of great use to everyone else, and it would also help with the transparency angle of the proposal if this somehow could be extended in a way that there could be a computation of how a particular ranking fares in terms of other definitions of fairness, right? So you could say that according to fairness star, you rank that high, but according to these other definitions, you're higher or lower. Because fairness is a notion that is quite tricky, and it's been actually discussed, right? So this is just a suggestion. It's up to you whether you will.
Yeah, sure. So what we are currently planning to do is to also have a user interface, because from the algorithm part, you do need the input of the minimum proportion anyway. And then you can say, like, okay, given you gave this parameter, then the ranking would look like that. You could even show, like, the comparison of the rankings.
You could standardize a template for people to define fairness metrics and then just do the computation and return it.
Well, I would say that given from all the fairness work, I know that this is a rather long-term thing to do. But yeah, good point.
Right. Thank you.